Okay, today we are going to discuss thin wall pressure vessels. Now, there are two types of thin wall pressure vessels. One is the spherical vessel on the left, and the other one is the cylindrical vessel on the right. These two are the common types of thin wall pressure vessels used. Now, if you look around you, you can find quite a number of thin wall cylinders and very few thin wall spheres. Okay, so example of thin wall cylinders that you can find is the drink can that you can buy when you buy your drinks, right? Pepsi, Cola, or Coca-Cola, all those cans. Those are made of thin wall aluminum and slightly pressurized. Okay. And in other places, in industry, you can find them in boilers or tanks. In general, we define a thin wall pressure vessel when we have the ratio of internal radius, right, to the thickness. That's the uh, definition that we use. When R over T is larger or equal to 10. So it must be at least 10 or above. Okay. In other words, in certain texts we use D over T, the diameter of the cylinder itself or the pressure vessel with respect to T, and this must be greater or equal to 20. Alright. Or in simple words, we say D is larger or equal to 20 times the thickness, or the radius is at least 10 times the thickness of the wall for the pressure vessel, right? Now, if we calculate using the approach that we are going to discuss, the error in the stress calculated is approximately 4% or less than the actual maximum stress in the vessel. This is based on experimental and research work done. Okay, so when R over T is 10, that is the lowest ratio you can go. The error is about 4%. So if you have a vessel where R is larger than 10T, meaning the ratio gets bigger, therefore the error will get smaller as well. Now, we have also some assumptions that we should make in our development process for the equation. First, we assume uniform or constant stress throughout the thickness. The stress distribution is constant throughout the thickness. Meaning, if you take the stress across the thickness of the wall, so we have the thickness of the wall, right, like that. Okay, this is inside, this is outside. So across the thickness, any location you take across the thickness, we assume that the stress distribution is constant. The stress is the same here and in the middle or anywhere within the thickness because it is very thin comparatively. The other thing that we assume is in our equation we will use gauge pressure, right? So in the equation that we are going to derive, we are using gauge pressure only. Now let's take a look at the first type of pressure vessel, which is more numerous, more commonly found, the cylindrical vessel. Now for this cylindrical vessel, or even for the spherical vessel, we have three parameters that we will use in our analysis. Only three. Number one is the wall thickness, T. Number two is the inner radius. So R is the inner radius. Okay, not the outer, it's the inner radius. So if you use D, so that will be inner diameter. Okay, inner diameter. Right. And number three is the pressure of the fluid inside the cylinder. Whether it's gas or liquid, is fluid. Okay. And so we use gauge pressure. P in our equation will be gauge pressure. And also in our analysis, we'll analyze somewhere remote or far from the ends, because at the end of the pressure vessel, you have weldings, you have joints, the thickness will change and so on. So it's not going to be accurate using the equation when we want to do it near the ends. So what we do is we choose an area far from the end, or we call it remove from the end. Okay. And then if we take an element, we'll find that we have two normal stresses in the longitudinal direction or lengthwise, which is sigma 2. We will show to you that it is sigma 2. And in the circumferential or hoop direction, which is sigma 1. So this is sigma 1. And in the circumferential, so it's in that direction. Okay, it goes around the cylinder. So it's called the circumferential direction, or also called the hoop direction. Remember hula hoop in school? If you have ever played hula hoop before, it's a ring, right? It's a circular rod. So that is why it's called hoop stress or circumferential stress. Sigma 2 is in the longitudinal direction. So it's in that direction there, longitudinal. Okay. Therefore, it's called the longitudinal stress. Let's take a look at the derivation for the first one, which is the hoop or circumferential stress, normally written in text as sigma c, right? So we have sigma c, and in certain text they write as sigma 1. Okay, what we do is, if you take a look at the cylinder itself, now the cylinder is going to be sectioned by three planes, three sectioning planes. A, the first one is A, the second one is B, and the third one is C. A and B are sectioning planes perpendicular to the length of the cylinder. Okay, and C is in the longitudinal direction or lengthwise, which will split the cylinder into two parts or two halves. So what we need is, we need just a portion of the cylinder which we have taken out. So we take out as shown in diagram B below. Now we know what is inside. Inside is the pressure. Okay, the pressure actually acts perpendicular to the surface, right? That's what you learn in physics. So the pressure is acting perpendicular to the surface. And within the material itself, if you take a look at this area here and the area at the bottom of the section, now on those areas, we will have sigma 1 of the circumferential or hoop stress acting on those surfaces. So we have one on the top and one at the bottom. Okay, is distributed over the area. So we have sigma 1. Inside we have P. Now the diameter is given as 2r, or 2 times the radius. Okay, that's the internal radius or internal diameter, and the thickness of the wall is T, right? So from this diagram here, then what we can do is we take equilibrium of forces in the sigma direction. Okay, you can call it uh, x direction. Okay, because the diagram above gives you x direction is in this direction. Okay, so that is in the x direction. So equilibrium of forces in the x direction, we have summation of forces is 0. That's why it's called equilibrium. And so we have two forces acting. One comes from the stress. Okay, one comes from the stress sigma 1. And you have two of them. So you have two times sigma 1 times area. Stress times area will give you force. So sigma 1 times the area. The area will be the thickness times the length, right? And the length of the section that we take is dy. So that is the area, and that is the stress. So sigma 1 times area becomes the force times 2. And that is towards x, towards negative x, or to the right in that direction. There we will have the pressure effect. Now the pressure is acting normal to the surface, the internal surface, or perpendicular to the surface. Therefore, the resultant of the force due to pressure, so that is F pressure, is equal to the pressure times the projected area that it is acting on. So the projected area in the x direction is equal to dx times the diameter, or 2r. Okay, so 2r is the diameter. That's the diameter. Sorry, not dx. dy is the length or the thickness of the segment. Okay, the length of the segment. So that gives you the area. So this is the area. And the stress is equal to P. The pressure is similar to a stress. It's acting on the surface. So we have then, if we simplify this equation, what do we do? First, you can divide by dy. Both sides of the equation, then you can terminate dy, right? Then you are left with 2 sigma 1 t dy, or t is equal to p times 2r. And if you simplify the equation, we will have this equation here, right? Sigma c is equal to sigma 1 is equal to pr over t. P is the internal pressure, r is the radius, and t is the thickness of the wall. Or in certain textbook, they will use d, so it's pd over 2t, right? So it's just changing d with r. Next, we take a look at the longitudinal stress, sigma L. So the longitudinal stress, sigma L or sigma 2. What do? We take the left portion of the cylinder. If we use the sectioning plane B, then we take to the left of sectioning plane B. Inside the cylinder, we have the pressure P, right? And along the wall, that is this area here, that is the section area, right? All around the wall. So that is the section area of the wall. Now, of course, on the section area, you have the stress sigma 2. And the pressure is inside, is acting on the rear plate or rear cover. Whatever the shape is, we know that P, the pressure, right, or this P here, is acting in that direction. So that is your Fp. And the force to the right in the y direction is due to sigma 2. So you have there, that is F due to sigma 2, due to the stress in the wall. So equilibrium of forces in the y direction. What do we have? We have Fp is equal to F sigma 2. Or in other words, we have sigma 2, that is sigma 2, the stress times the area, that is the area of the annulus around the cylinder wall. Okay, 2 pi r is length of the circumference of the inner radius, and you just times by the thickness to get the area. Now, some of you might be wondering, why can't you just take the outer area, right, using the outer diameter, and minus the hole in the middle? Yes, you can do that and you get a more accurate answer probably, but your equation is going to be more difficult to use. All right. So since the error has been proven to be 4% or less, then the answer that you get will be acceptable in engineering work. Okay, simple engineering work. So don't bother about having pi r square, where r, the first r is the outer radius, right? You can use a is equal to pi r squared minus pi r squared. But then your equation will be more difficult to solve, right? So we don't want this. It has been proven that this is not required because the error is 4% or less, right? And Fp here is Fp, here is F sigma 2, okay? So the area now is the circular area inside, so it's pi r square, and times the internal pressure. So you have this equation here, which you can simplify to get the final equation of sigma L, the longitudinal stress in the walls, is equal to sigma 2 is equal to PR over 2T, or in other text is written as PD over 4T. Okay. Now we go to the spherical vessel. For a spherical vessel, you just need to take one section. Anywhere you take it passing through the centroid of the sphere will give you a hemisphere, as shown in the figure B. Okay. So if we take a look at the hemisphere, we know that inside the hemisphere, there's pressure P. So you have the pressure P inside. Along the section in the wall, this looks similar to the longitudinal stress in the cylinder, right? So if we solve this, summation of forces in the y direction is equal to 0, then we get the same answer as in the longitudinal stress for cylinder, except that here this is sigma H or sigma C, okay, sigma circumferential. And we see that there's a difference between the stress in sphere. There's only one, because in any direction you go is circumferential. There's only one. There's no longitudinal direction. So what we do is in a sphere we only use one equation, And so, if you compare, this equation is the same as the longitudinal stress equation for thin cylinders, right? So we'll have a look in an example what effect that has. So in this example, we have a cylindrical pressure vessel, it says, with an inner diameter of 1.2 meters, that's diameter, and thickness of 12 millimeters, right? So what we have is, this is D, diameter of 1.2 meters, and we have thickness T of 12 millimeters. Now the question says determine maximum internal pressure. What is the maximum internal pressure? And that is P, right? The pressure P. What is the maximum pressure you can put inside the cylinder? So that neither its circumferential nor its longitudinal stress components exceeds 140 megapascal. So that is the limiting stress. Okay, remember in solid 1, that can be considered as the allowable stress. So that is sigma allowable. Okay, and then it tells you the second part of the question, if you have a spherical vessel which is similar size. What do you mean by similar? Similar means the diameter is the same and the thickness of the wall is the same. Now, what is the maximum internal pressure that it can sustain if it is a sphere and not a cylinder? So we have two parts to this question. Let's look at it as the cylinder. For the cylinder, we have two equations, right? One, we have sigma H or sigma C is equal to PR over T. The other one is sigma L is PR over 2T. Now looking at these two equations, we will know immediately that the stress will be higher here by a multiplier of 2, right? For a constant pressure, for a certain pressure value. So this is equal to 2 times sigma L for a cylinder. So you don't need to do two calculations. Just calculate for sigma H, which will give you the largest stress, because we have a limit, stress limit or allowable stress, and that goes into sigma H. So sigma H or sigma 1 is PR over T, and the only unknown we have in the equation is P, which gives us P is 2.8 newtons per square millimeters, or in other words, this is megapascal, right? Millimeter square is 10 power minus 6. So Newton per meter will be Newton over meter times 10 power 6 or megapascal. So the pressure can go up to 2.8 megapascal only before when the stress sigma H reach 140 megapascal. So if you want to calculate for the longitudinal stress, you can do so. Okay. Now, you might be asking why we say the atmospheric pressure is negligible. So the atmospheric pressure is 2.8 megapascal. Sorry, not atmospheric pressure, the pressure inside the vessel. The atmospheric pressure is even smaller. So 2.8 megapascal comparatively with sigma 1, which is 140, and sigma 2, which is half that, right? 70. So this is very small, and so it is neglected. Okay, it's insignificant. Okay, for the spherical vessel, we know that the equation for spherical vessel is equal to the or similar to the longitudinal stress equation for a cylinder. So we have sigma 2 is equal to PR over 2T. So using the equation and with P as the unknown, we will get P is 5.6 megapascal, the same as the value if we find the longitudinal using the longitudinal stress equation for a cylinder. Now here we can see that the spherical pressure vessel can carry twice as much internal pressure as a cylindrical vessel. So if you want to carry a liquid which is having twice the internal pressure, then you might as well use a spherical vessel because it will be the same thickness and the same diameter as a cylinder. However, if we have less volume that it can carry, right? So you don't want to buy Coca-Cola spheres, okay? You get less than half the drink than when you buy a can of Coca-Cola, right?